Hi everyone, Davor here. In this video, I will introduce PSSLab, a software package designed to provide a comprehensive set of tools for tuning and verifying Automatic Voltage Regulator (AVR) and Power System Stabilizer (PSS) parameters. PSSLab was developed using MATLAB Simulink of MathWorks and is based on the state-space small signal stability approach in the frequency domain. This methodology is applied to model the generator, excitation system, power system, and power system stabilizer. So let's get started. After a double click on the PSSLab icon, an initial form appears on the screen with menu items file, AVR tuner and PSS tuner. From the menu item file, I will now open a project which parameters were previously saved under the file name 240 MW turbo. Subsequently, a new form of generator parameters appears on the screen, including project name, generator type, and the main generator parameters such as rated apparent power, rated terminal voltage, rated frequency, rated speed, and rated cos phi. You can see that each of parameter is described with its label, its value, its unit, and a short description. Furthermore, the following generator parameters are given: the generator reactances in the direct axis, the generator reactances in the quadrature axis, stator leakage reactance, stator resistance, transient time constants in the direct axis, transient time constants in the quadrature axis, and finally the inertia coefficient, including generator and turbine rotating masses. After an overview of the generator parameters, we also need to review the exciter parameters. Click on the next page to open a new form with exciter parameters, which includes rated field current, rated field voltage, ceiling current and its duration, ceiling voltage, air gap field current, no load field current, rotor winding resistance at certain degree, and excitation transformer secondary voltage. In case of an exciter machine such as brushless exciter, the parameters of the exciter machine are also considered. However, in this video, we will restrict only to the static exciter. This form also includes a so-called open circuit characteristic, which is necessary later on to determine the operating point of the generator. Based on the data given in the data sheet or from the measurements, the open circuit characteristic can be simulated, and then we get the curves. The blue one with the OCC characteristic, open circuit characteristic, and the red one with the air gap characteristic. As you can see, in the x-axis we have the field current in per unit, and in the y-axis we have generator terminal voltage in per unit. Well, we still haven't completed the overview of all parameters, so we click on the next page, and the new form with the unit transformer parameters and grid parameters appears on the screen. The unit transformer parameters include rated apparent power, rated primary voltage, rated secondary voltage, reactance, and resistance. The grid parameters are usually given in the form of the maximum and minimum short circuit current, or in the form of the maximum and minimum short circuit power. In this case, they are given in the form of the maximum and minimum short circuit current and it is referred to the 275 kilovolt grid voltage. In addition, maximum and minimum grid impedance are given with their resistances and reactances, and they are in ohm. All these grid parameters have to be converted into the generator base, so that we have the maximum grid impedance on generator base and minimum grid impedance on generator base. How do we do this? We just simply click on the execute conversion and then we get this data. At the end, we just close the parameter entry and we come back to the initial form. Now, the next step is to tune the AVR parameters. From the menu item AVR Tuner, we can select a few different types of AVR models which are based on the IEEE standard 421.5. IEEE standard 421.5 is a recommended practice for excitation system models for power system stability studies. For this video, we will work with ST7C model. After selection of the ST7C model, a new form with all relevant parameters for this model appears on the screen. I can now show the model diagram in IEEE standard 421.5 ST7C model to illustrate the correlation of the parameter labels in form with model diagram. For example, in model diagram we have here kPa, and in the form we have kPa also here, voltage regulator gain. In conjunction with the model diagram, we can have an overview of the simplified simulation diagram consisting of the AVR and the thyristor converter as the consistent parts of the exciter and the generator as the part of the process in the closed control loop. The open loop or closed loop frequency responses are simulated in full speed no load operation by the perturbation of the delta VT, generator terminal voltage as an output, and the perturbation of the delta V injection as the input into the summing point. To start the simulation, I need to enter the wish phase margin. So I enter here 60 degrees, for example, and then click on the open loop simulation and click on the calculate model parameters and simulate frequency response. An open loop frequency response plot appears on the screen, and all calculated parameters fill in the text boxes in the form. There are two graphs, one for the magnitude in decibel and one for the phase in degrees. The blue lines are simulated with unsaturated reactances, whereas the red lines are simulated with saturated reactances. The gain and the phase margin can also be displayed and verified. So here is the gain margin and here is the phase margin. Similarly, we can simulate the closed loop frequency response plot. I just choose here the closed loop and click on the calculate model parameters and simulate frequency response. We've got here the frequency response of the closed loop with magnitude in decibel for one graph and the phase in degree for another graph. The blue line is for the simulation with unsaturated reactances and the red one is for the simulation with saturated reactances. The peak values on the magnitude graph can also be verified. Here we got the peak values MP with corresponding frequencies Fp. Having taken a closer look into the form, we can see that all parameters of ST7C model have been shown in the text boxes. On the right part of the screen, we have the control parameters obtained from simulation with unsaturated reactances, here in the left column, and for simulation with saturated reactances, here in the right column. These control parameters such as gain margin, phase margin, maximum amplitude in the closed loop are important to ascertain the quality of the frequency response and compare with those given in IEEE standards for excitation systems. We can notice the control parameters with saturated reactance provide slightly more gain and phase margin. For example, the difference in the phase margin is around 6 degrees more with saturated reactance. Compared with unsaturated case, the model with saturated reactance is more complex. It uses a sixth-order linearized generator model. We can finally start to tune the PSS parameters. From the menu item PSS Tuner, I will choose the pre-filtering. A new form appears on the screen for which we can say few preliminary words using model diagram. So I click on the Show Model Diagram. This model diagram is based on IEEE Standard 421.5 Type 2C, which is widely used PSS model type. It essentially consists of two major parts. The first part is the pre-filtering, here in the blue frame, and the second part is the gain and the lead lag blocks. At first, we are focusing on the pre-filtering part of the PSS. It has two separate inputs, VSI1 for the rotor speed or frequency and VSI2 for the generator electrical power. The first signal of rotor speed passes through the low-pass filters in so-called washout blocks, then transducer, and then through ramp tracking filter. The second signal of generator electrical power passes through the washout blocks and integrator. Then the signal is branched into two pathways, one to be summed with the output of the transducer through KS3, and one directly to the minus input of the summing point. We can follow the path in the model diagram. Finally, the both signals are subtracted in the summing point. At the output of the summing point, a so-called synthesized speed signal is obtained. This synthesized speed signal is equivalent to the integral of acceleration power. This is why in some literature this kind of PSS is also called the integral of acceleration power PSS or IAP PSS. Now in the form for the pre-filtering we can enter the frequencies ranges of oscillation which may be expected during the operations. So for the inter-area oscillations I will enter from 0.2 to 0.5. These values are mostly given by the grid authorities. For the local oscillations I will enter from 0.8 to 1.5, and for the torsional oscillations I will enter from 10 to 15 Hz. The values for the local and the torsional oscillations are usually given by the OEM. Now here right, I will select one of the Bode plot. For example, I will select the Bode plot or frequency response plot of the ramp tracking filter and just click on the calculate parameters and simulate the Bode plot. The graph of the Bode plot or frequency response plot of the ramp tracking filter appears here on the screen. Here left, the values of the calculated time constants, gains and other parameters which are relevant for the pre-filtering are provided in the text boxes. Let me show you one more frequency response for integral of accelerating power. For the proper settings of the pre-filtering, the phase of integral of accelerating power should be passing around 0 for all frequencies of oscillations in which PSH should provide good damping. So you can see here from, for example, 0.1 Hz to even 100 Hz, we have passing the phase around 0. In this video, it is not intention to go into the physical and mathematical details, but only to provide overview and merits of PSSLab software. Indeed, there will be a series of videos with in-depth explanations for each topic separately. The next step is to tune the PSS compensation. Again, from the PSS tuner, I select the phase compensation. The form for tuning of the phase compensation appears on the screen. We open the model diagram to explain which blocks are pertinent to the phase compensation. Here inside of the green frame, we can notice there are 4 lead leg blocks. The first 2 are referred to so-called PSS type 2A. So this is the first block, this is the second block. By adding a third block, we get the PSS type 2B, and if all 4 blocks are included, we get the PSS type 2C. For the better understanding the tuning methodology for phase compensation, let us have a closer look into the simulation diagram. So I open here the simulation diagram. The blocks in gray are the consistent part of the exciter, including essentially the AVR, the thyristor converter, and the power system stabilizer. PSS is shown here with 4 blocks: calculated delta omega and delta P electrical, pre-filtering, KS1 as a PSS gain, and the PSS lead leg blocks. The blocks in blue are the generator, the unit transformer, and the grid. The exciter as a controller and the generator as a process are here in the closed loop, which purpose is to regulate the generator terminal voltage, VT, based on the error signal, which is the difference between the reference and the measuring signal. However, the unit transformer and the grid are also taken into account as the part of the entire process. As already mentioned, for this video we are using the control algorithms based on ST7C for the AVR and PSS2C for the power system stabilizer. So the basic idea is to obtain the frequency responses for the perturbations of the delta VT of the generator terminal voltage as the output and the perturbations of the delta V injection as the input to the AVR summing point. Indeed, 2 responses are simulated. The first, the uncompensated phase with PSS off, and the second, the compensated phase with PSS on. In later case with PSS on, the most appropriate parameters of lead leg blocks are ascertained during simulation. The target is the PSS lead leg blocks should compensate the phase leg of the uncompensated response in the range of the frequency of interest, which are generally between 0.1 Hz and 3 Hz. After this theoretical background, we can work out the phase compensation. First, we need to enter the various operating points. So I have already entered 5 operating points. Active power for all 5 operating points is 240 megawatt, whereas the reactive power is different. The first operating point 148.5 megawatt, which is the rated operating point, then 100 megavar, then 50 megavar, then 0 megavar, and finally minus 50 megavar. Then here we confirm the operating points for which the simulations will be performed. So I select now all of these operating points. And then I select the AVR type ST7C, and finally I can click on the Simulate Uncompensated Response. Let me first close the frequency response plot and focus on the results of the obtained field currents. Here are the results of the obtained field currents for each operating point. These results should serve to verify that the obtained field current is nearly equal to the values given in the technical data sheet and/or measurements. This also indirectly verifies the values of synchronous reactances, stator leakage reactance, stator resistance, and the open circuit characteristic, because the field current is derived from the reconstruction of the generator phasor diagram at certain operating point. Furthermore, this will give confidence that the parameters of the sixth order generator model after linearizations are okay. You can see that at rated operating point the obtained field current is around 2185 amps, whereas the value in the data sheet is, let us check from the parameter forms. So in the parameter form is the 2150 amps rated field current. So the difference is just around 1.5%, and this is the small difference which is acceptable. Finally, let us pay attention to uncompensated frequency response, and in particular to the phase lag which needs to be compensated with lead lag blocks. Let us zoom into the phase of the frequency response. We can see that the phase lag or delay is obviously different for the different operating points. So for example at 1 Hz, we have the phase lag around minus 50 degrees for rated operating point P1, Q1, and around minus 65 degrees for operating point P5, Q5, when the generator is absorbing the reactive power of minus 50 megavar. Now, the target of the lead lag blocks is to compensate the phase lag. In this video, we will use the PSS2C to simulate the phase compensation. First, I select the PSS type 2C, then all 4 lead lag blocks become visible. Then I click on Simulate Compensated Response 2C. A frequency response pops up on the screen with 3 curves. The blue one, which is the uncompensated frequency response, the yellow one, which is the compensated response, and the red one, the response of all 4 lead lag blocks. Here left, we've got the parameters of all 4 lead lag blocks. Similarly to previous simulations with maximum grid impedance, ZE max, we can also initiate the simulations with minimum grid impedance, ZE min. And here we get a slightly different frequency response and also slightly different parameters of the lead lag blocks. If we only pay attention to the graph of the phase, we can notice that the compensated phase is passing around the 0 in the range of the frequencies where the PSS should provide a good damping. Between 0.1 and 3 Hz. And if we set the criteria that it shouldn't exceed plus minus 10 degrees, we can see that this criteria is fulfilled from approximately 0.06 Hz to almost 8 Hz. To conclude, the phase response of the lead leg blocks is simulated in a way to shape the compensated curve around the zero along the entire frequencies of interest. As already mentioned, the frequencies of interest in which the PSS should provide a good damping are generally between 0.1 to 3 Hz. The last step in PSS tuning is to determine the KS1 gain. From the PSS tuner, we choose the KS1 gain calculation. The form for tuning of the KS1 gain appears on the screen. Again, from the model diagram, we can see the KS1 block here in red, which is just before the lead leg blocks. And in simulation diagram, we have added KS1 block and P electrical calculation block, which are in gray. Therefore, these two blocks are consistent part of the exciter. Now, the target is to ascertain the natural or uncompensated damping and compensated damping with PSS on, which are correlated with the perturbation of the generator active power, P electrical. Accordingly, the transfer function is now simulated for the ratio of the perturbation of the delta P electrical and the perturbation of the delta V injection in the summing point of the AVR. I have already entered 10 different operating points for which the simulations will be conducted. So there are two levels, 240 megawatt and 180 megawatt. For each level we have separately 148.5 megavar, 100 megavar, 50 megavar, 0 megavar and minus 50 megavar. Let us select the maximum grid impedance, enter KS1 equal to 5 and click on the Initiate Eigenvalue Analysis. After the simulation is completed, different sorts of results pop up on the screen. First, let us look at graphs of the initial response of P electrical, so generator active or electrical power, for all 10 operating points. One graph for each operating point. This response is in time domain and it is for the linearized model shown in the simulation diagram. The oscillations in blue are for the response with PSS off and in red for the response with PSS on. Both responses decaying, indeed the red one with PSS on faster but still not enough fast. The figure 1 is the response on initial conditions for P1 Q1 operating point. And we can check out also for other operating points, such as P1 Q2, P1 Q3, and so on until P2 Q5. The responses are similar, however, there are some differences in frequency of oscillations and amplitudes. Since we are not happy with the slow decay of the red curve with PSS on, we try to increase the KS1 from 5 to 10, for example. So I write here 10 and click on Initiate Eigenvalue Analysis. Indeed, we've got much faster decaying and only few oscillations of the initial response with PSS on. However, we want to have only 2 oscillations, so this is the first one and the second one, with the second amplitude considerably smaller than the first one. So we increase KS1 from 10 to 15 and then initiate eigenvalue analysis. And here we are. We've got responses for the first amplitude, second amplitude, which is considerably smaller than the first one, and maybe the third one, which is to be neglected. And indeed, for all 10 different operating points. Let us check it out. Now, let us have a closer look into the frequency response of the damping, which is the ratio of the perturbation of the delta P electrical and the perturbation of the delta V injection. The blue curve is for the response with PSS off, and the red curve is for the response with the PSS on. The response with PSS off is much higher in amplitude for the range of the local area of oscillations. The response with PSS on is well below, which provides a good measure of the damping. The ratio of the maximum amplitudes with PSS off and PSS on should be at least 3 times. The phase responses appear to be symmetrical at the crossover frequencies. We can see that the curves are approaching to each other toward the lower frequencies, and in one point they intersect at 0.208 Hz. Similar observation can be shown for the frequencies for the range beyond local area oscillations, where the point of intersection is 1.89 Hz. We can improve this with further tuning of lead lag blocks and by further increasing of the gain KS1. The target is to have the intersections equal or beyond the frequencies of oscillations for which the PSS has to be effective. For example, from 0.2 Hz to 2.5 Hz. Remember from the menu item pre-filtering, the minimum given frequency of oscillations in inter-area region was 0.2 Hz. So let us reopen the phase compensation form and increase T1 in the first lead lag block from 0.18 to 0.22. Increase T3 in the second lead lag block from the 0.043 to 0.05 and increase T31 in the fourth lead lag block from 0.0169 to 0.02. Then click on Manual and click on Simulate Compensated Response 2C. Now we can zoom into the phase from 0.05 to 10 Hz and verify that the response is still within plus minus 10 degrees in the range of the frequencies of interest. That should be okay. Close the border plot, close the form, and open the KS1 gain calculation. Increase KS1 from 15 to 18 and initiate eigenvalue analysis. Then zoom into the magnitude at low frequencies. The intersection has shifted from 0.208 to 0.173 Hz. On the higher frequencies, the intersection has shifted from 1.89 to 2.62 Hz. Accordingly, the frequency response with PSS on is below the response with PSS off for the entire targeted range from 0.2 to 2.5 Hz. This form also provides an overview of the eigenvalues of the state space matrix, here in the left column for PSS off and in the right column for the PSS on. The state space matrix with PSS off is of the 8th order, therefore it has 8 eigenvalues. 2 of them are complex conjugate pair, the 5th and the 6th. The state space matrix with PSS on is of 13th order, therefore it has 13 eigenvalues. 4 of them are complex conjugate pair, the 8th, 9th, and 11th and 12th. The complex conjugate pair with PSS off has a small real part, minus 0.231, and imaginary part 5.892 radian per second, which is the oscillation frequency. With PSS on, the real part has substantially increased to minus 6.174 and the imaginary part is 4.583 radian per second. The damping coefficients are also shown here in separate text boxes in units so-called Neper per second for the maximum grid impedance and separately for the minimum grid impedance. Indeed, we can also initiate the eigenvalue analysis for minimum grid impedance. And again, the simulation results pop up on the screen for the initial response in time domain and for the damping in frequency domain. So the values are minus 6.17 Neper per second for the maximum grid impedance and minus 7.39 Neper per second for the minimum grid impedance. Thank you for watching. If this video helps you, please give it a thumbs up and consider subscribing for more videos related to the topics of power system stabilizer. Bye for now.